Hello, welcome to a video on section 5.4, part 1. We're going to pick up this video from example 2. Example 2 is asking to integrate from 1 to x of t minus 1 times dt. So, if you think about t minus 1, that's just a linear function, right? With y-intercept of negative 1 and a slope of 1. So let's go and plot that. Okay, very easy, right? Now, we're integrating it from 1 to x. Well, again, x is going to be our upper limit, and a of x is our area of our region from 1 to x. So say, for example, I'm integrating from 1 to 1. Then I expect my area to be 0, right? Because there's no region sweeping through. But what if I'm integrating from 1 to 2? So looking at this region right there. Well, that's going to be a right triangle with base of 1 and height of 1. Remember, area of a triangle is 1/2 times base times height. So that's going to be 1/2. Okay. What if I go from 1 to 3? Now in this case, my right triangle will have a base of 2 and a height of 2. Again, area is 1/2 times base times height, so that'll be 2. And then lastly, what if I'm integrating from 1 to 4? So you can see how the area is accumulating, right? It's getting bigger and bigger as x gets further away from 1 from the right side. So the base is 3, height is 3, 1/2 times base times height. We get 9/2, or 4.5. But what if I go in the other direction? This is where things get a little bit interesting. What if I go from 1 to 0? So now I'm looking at that region. Well, one thing to keep in mind is when you integrate from 1 to 0, it's a negative of integrating from 0 to 1 of f of t times dt. Now in this case, the area is beneath the x-axis, so we think the area should be negative, but we're also integrating from right to left. So we know the area from 0 to 1, if we were to integrate that, is going to be negative half from 0 to 1, right? Because you go from left to right, and the area is below the x-axis. But because we're integrating from right to left and we're below the x-axis, that's like a double negative. Because we're below the x-axis and we're integrating from right to left. So in that case, you're going to get negative half. Sorry, positive half. You get two negatives, right? Because you're below the x-axis and you go from right to left, so it's positive half. Sorry about that. And if I'm integrating from 0 to negative 1, so it's like this here. Base is 2, height is 2. 1/2 times base times height, you're going to get positive 2. So again, it's a double negative. But here's the question. How would I express my area as a function of x? So in the previous example, example 1, we saw there was a linear relationship. As x went up by 1, y went up by 4, and we were able to figure out what that linear relationship was. I think it was 4 times x plus 2. So it's not quite as easy to figure out here. We do see some sense of a pattern, but it's definitely not linear because when x goes up by 1, or area is not going up by a consistent amount. Like, sure, we go from 1 to 2, area goes up by half, we go from 2 to 3, that goes up by 3 halves. So it's a little bit tough, tricky to figure out. But one thing we could think about is that we could try to do this geometrically, right? If that's at 1, we'll say that's at x, and we have this right triangle, right? Now, again, this is the equation y equals 2 minus 1. So this point that I'm drawing, in terms of x, would be x comma x minus 1. That's because, again, x is right here, so we just get a straight shot up to that point. So it's going to share the same x coordinate. And if you put an x into your expression here, right, you get y equals x minus 1. So the area of this triangle is pretty easy. That's going to be base of x minus 1. That's going to have a height of also of x minus 1, because you're going from a point of y equals 0 to a point of y equals x minus 1. So our area is 1 half times x minus 1 times x minus 1. Or if you were to go a bit further, 1 half parentheses x squared minus 1. Oops, sorry. X squared minus 2x minus 2x plus 1. So we did this earlier on Sunday morning. 1 half x squared negative x plus half. So I could get my area geometrically, right? My inspection was a little bit harder to tell from the table, but geometrically that wasn't so bad. Or you can use anti-derivatives, like in example 1. And that's leading us to this is kind of building up to formula theory of calculus that we're going to discuss in a little bit. So if I did anti-derivatives, remember the antiderivative of t minus 1 is not so bad, right? It's t squared over 2 minus t plus a constant, right? Now, if I were to plug in x in 1, or plug in x first, and then plug in 1 second, what do we get? X squared over 2 minus x, and half minus 1 is negative half. You have a negative before it, so plus half. Oh, you get the same thing. So again, the way we're evaluating this, because remember we're going from 1 to x, so we plug an x in for t, and plug 1 in for t, and subtract. So we get the same thing. And we see it right here, right? The integral from 1 to x minus 1 times dt is half x squared minus x plus half. Now, this is what we're going to be working our way towards, the fundamental theorem of calculus, or FTC for short. What if I take the derivative of an antiderivative? So that's what this is, right? It's the derivative of an antiderivative. Because remember, the integral represents an antiderivative. Well, it would be the same thing as taking the derivative of all this, right? Because that was what the antiderivative equaled. If I take derivative, then I'm getting 1 half times 2x minus 1 plus 0, or x minus 1. So that's interesting. So it seems as if I take the derivative of the antiderivative, oops, sorry, I should be t. Okay, I'll just erase that. Okay, I'm still recording. I was getting a little worried there. My computer froze up for a bit. Perfect. So if I take, excuse me, if I take the derivative of the antiderivative, it's almost like I'm replacing t with x. So in essence, if f of t minus 1, f of x, of course, to be x minus 1, it seems as if taking the antiderivative from a constant to x is just f of x. And that's the fundamental theorem of calculus part 1. So, in the second part of FCC, we'll talk about in class on Monday. But if f is a continuous function on an interval from a to b, and capital F of x equals this, then I'll have a derivative at every point in x in AB, and the derivative of your antiderivative will just be little f of x. Or actually, I think I meant to put here d dx of a constant x of f of t times dt is going to equal f of x. So derivative antiderivative equals f of x if you're integrating from a constant to x. So there are some implications of the fundamental theorem of calculus part 1. First off, every continuous function is a derivative of some other function. Also, every continuous function has an antiderivative. And we know this because if little f equals the derivative of an antiderivative, you know, every function, or every continuous function that derives some other function, every continuous function has an antiderivative. The antiderivative f of x will also be continuous on from a to b, since the antiderivative exists. And we know that if a function is differentiable, it must be continuous. Remember, all differential functions are continuous. So which means that this guy right here will be continuous on a to b, provided that f is also continuous, and the processes of integration and differentiation are inverses of each other. Now, something to keep in mind when you're doing these problems is that it doesn't matter what the lower limit is, just as long as it's constant. As long as it's a constant, because if you were to say integrate, for example, just being hypothetical, 1 to x of x times of x over 2, that's what I'd say. The answer to that would be x squared, right? No, sorry, let's say 2x. The answer would be x squared. If you plug in x and 1, you get x over 2 hold on a sec. Minus 1/2, or if you do t, actually, let me take that back here. Sorry, I totally botched this one. So you're integrating from 1 to x of t times dt. So you have t squared over 2 plus c as your antiderivative. If you're going from 1 to x, it's basically going to be x squared over 2 plus c minus 1/2 plus c. Do you mind just saying x squared over 2 minus half? Now, if you're integrating, and then if you take the derivative path, then I just came back to 2x. or sorry, 2x over 2, which is just x. But if you change the lower limit to a different number, you have all these changes here, right? But when you do that, you still get back to just x. So that's why the lower limit's not going to matter, because it's going to go away anyway when you went to the derivative and antiderivative. Remember, we're doing a derivative of an antiderivative. So the lower limit doesn't matter. So in this case, you get just sine x here and just sine x here. So in the case of example 2, that's just going to be 5 over 3 plus x squared. Just replace x with t. So replace t with x. Or in this case, if you reverse it, because you have a constant at the bottom, that'll be negative secant x. Now things get a bit weird when your upper limit is not a plane of x, but it's a function of x. So in this case, our upper limit is not plane of x. So let's go back and take a look at this example I did a little earlier. We're going to go from 1 to x of t times dt, right? So the integer of that was t squared over 2. You put in 1 in x, you get x squared over 2 plus c minus 1/2 plus c x squared over 2 minus half, right? Now, if you were to integrate that, right? So I have that to the dx bit as well. Of course, the integrate that with respect to x. What's going to happen is that you wind up just getting just x. Now, what if I change to x squared? So it becomes x to the 4 power, right? Over 2, so c. And then c minus half of c. Now to do that, I'm working four x cubed over 2, which would be 2x cubed. So it seems as if I have to replace the t with x squared. So in this case, instead of saying that f of x equals x, f of x will equal x squared. But it also seems as if I'm multiplying it by the derivative of x squared. So x squared times 2x, or 2x cubed. Because when we do the antiderivative, as we saw here, the antiderivative is like replacing t of x. So you kind of do the same thing, but now you're replacing t of x squared. But you're also multiplying by the derivative of x squared. So it's kind of like chain rule in a way. So it's f of g of x to replace t with g of x, but also going to multiply by the derivative of g of x. So in this case here, our derivative is just going to be tangent of the square of 5x cubed minus 3 times 5x cubed times 5x cubed derivative. So in this case, I'm getting a tangent of 25x6 minus 15x cubed, and of course times 15x squared. So that's how I would do that. So again, replacing t with 5x cubed, but also because it's not plane on x, I got to multiply the antiderivative. We didn't do that before because, of course, sorry, multiply by the derivative of 5x cubed. So I didn't do that before because the derivative of x was just 1, so it didn't really matter when that derivative was x. But now because represents not the same with x, I have to multiply the derivative of that. Okay, let's get one more here. We'll end this video. So here now we're integrating for 5x x squared. So this is not a constant, of course. So what I could do is I could rewrite it like this. Integrate from 5x to a of sine 3t times dt plus a to x squared sine 3t times dt. And again, we pick any constant a that's between 5x and x squared. So we know this can make sense, because we've seen, we broke up integrals like that before, like we integrate from 1 to 4 of some function, right? We could take from 1 to 2 plus 2 to 4. That's not a big deal. We've done that before, right? And that was in 5.3 with the properties of integrals. And if I reverse this, so it's from a to 5x, again from a to x squared, that's dt. So now let me replace t with 5x. So we have negative sine 5x times the antiderivative. Sorry, why I keep saying that? Times the derivative of 5x. Sorry. Times 5 plus sine 3 times x squared. Because remember, what I'm doing now as well, is I want to take the antiderivative of all this. Sorry, I want to take the derivative of all this with respect to x. So when you do that, you replace t with whatever that limit is. And I might be just getting, it should be 15x, by the way. So negative sine 15x times 5 plus sine 3x squared times 2x. So negative 5 sine 15x plus 2x times sine 3x squared. So again, what I do is I broke up the integral, and remember taking the derivative of all this, right? With respect to x, I'm doing the derivative and the antiderivative. But if I break up the integral first, for 5x to a and 8x squared, reverse 5x to a, so it's from a to 5x. Using the fundamental theorem of calculus part 1, replace t with 5x. For the first integral, replace t with x squared for the second integral, and then multiply by the derivative of the upper limits. Derivative of 5x is 5, derivative of x squared is 2x. And of course, I have my answer. Okay, so I'll end the video, and then we'll pick up part 2 when we see each other again on Monday.